Section: Introduction. In this section, we delve into the realm of image retrieval, a well-known challenge in computer vision with various practical applications like visual search, object localization, and re-identification. The complexity of images often leads to ambiguous definitions in this task, where similar images can differ in crucial aspects, and different images can share similarities. Users often have multiple search intents when using a single query image, indicating that mere image relevance is not enough for accurate search results. For example, if we search with an image of the Burj Al Arab Hotel in Dubai, a user might be looking for other attractions in Dubai or an interior view, each related differently to the query image. Therefore, incorporating text instructions that express search intents is crucial for improving retrieval accuracy. Models should be able to understand various real-world search intents conveyed through open-ended text instructions, covering a wide range of topics and concepts. Existing models are usually optimized for specific domains, defining visual similarities manually or relying on predefined instruction templates. However, these approaches struggle to effectively model open-ended instructions. To address this, we introduce MagicLens, a set of self-supervised image retrieval models trained on a diverse range of query image, instruction, target image, triplets reflecting natural semantic relations mined from web pages. By leveraging large multimodal and language models, we refine open-ended semantic relations expressed in instructions. Our method constructs a large-scale training dataset with 36.7 million high-quality triplets, where models are trained to retrieve images based on a query consisting of an image and an instruction. MagicLens outperforms prior state-of-the-art methods on various benchmarks, including multimodality to image and image-to-image retrieval tasks, while maintaining or even improving text-to-image retrieval performance. Despite being 50 times smaller in size, MagicLens excels on benchmarks like SURSO, Domain Transfer ImageNet, and GeneCIS. We further evaluate MagicLens on a vast retrieval pool with 1.4 million unseen images using human-written search queries with diverse instructions. The results show that MagicLens can effectively handle complex search intents, surpassing previous state-of-the-art methods. Our contributions include introducing a novel approach for image retrieval using naturally occurring image pairs from web pages as training signals, developing an efficient pipeline to construct a large training dataset, and showcasing the effectiveness of MagicLens models in capturing diverse search intents. Section Summary. In this section, we introduce the challenge of image retrieval in computer vision, highlighting the complexity of defining image similarities due to diverse content. We propose MagicLens, a self-supervised image retrieval model trained on a large dataset of query image, instruction, target image, triplets mined from web pages to capture diverse semantic relations. MagicLens outperforms prior state-of-the-art methods on various benchmarks by effectively incorporating open-ended text instructions to enhance retrieval accuracy for complex search intents beyond visual similarities. Section: MagicLens. In this section, we construct data for self-supervised training. We find image pairs from web pages to train our models. First, we group and clean images from the same web page, removing noisy or irrelevant ones. Then, we expand metadata by adding alt texts, image content labels, and captions to provide more information about the images. After that, we score and filter the image pairs based on their relevance, keeping only the high-quality ones. We generate open-ended instructions using this metadata to connect the paired images effectively. Our model, MagicLens, has a simple design with shared parameters for vision and language encoders. We use self-attention layers and a multi-head attention pooler to integrate different modalities and create embeddings for matching. During training, we use a contrastive loss to update the model by comparing paired images against other targets in each batch. We also introduce additional negative examples to improve the training process. Overall, our approach results in 36.7 million triplets for training the self-supervised image retrieval model. For more details on the model design and training process, please refer to the appendix. Section Summary. In this section, we introduce MagicLens, a model designed for self-supervised training using web data construction. By mining image pairs from web pages and generating open-ended instructions with large language models, LLMs, we create a dataset of 36.7M triplets for image retrieval training. MagicLens employs a dual encoder architecture with self-attention layers and a multi-head attention pooler, trained with a contrastive loss function to match query target pairs efficiently. Section: Experiment Setup. In this section, we set up experiments, choose benchmarks, and select metrics to evaluate MagicLens' ability to retrieve images from different modalities. We focus on 3 tasks: composed image retrieval, CIR, domain transfer retrieval, and conditional image similarity. Each task involves specific image relations. We use 5 benchmarks to assess these tasks. For composed image retrieval, we use benchmarks like FIQ, CIRR, and SURSO to test the model's adaptability to different domains and its performance on real-world images. We measure recall for different subtasks in these benchmarks. SURSO, with multiple ground truths for each query and a large image set, is our main benchmark, where we use mean average precision, MAP, for evaluation. In domain transfer retrieval, we use the Domain Transfer ImageNet (DTIN) benchmark to retrieve images from different domains but with similar objects as in the query image. We report recall for various subtasks in this benchmark. For conditional image similarity, we use the Gene CIS benchmark, where models need to find similar images based on specific keywords related to the query image. We report results for different subtasks in this benchmark. We compare MagicLens models with other baselines across these benchmarks. Our observations show that both CLIP and COCA-based MagicLens models outperform previous models significantly, especially on challenging benchmarks like SURSO and DTIN. We provide detailed results in the appendix. Additionally, we find consistent performance improvements when comparing different versions of MagicLens across the benchmarks. This indicates the high quality of the data and the scalability of the model architecture. Furthermore, although MagicLens models are trained for tasks involving text instructions to retrieve images, they can also perform image-to-image retrieval tasks by providing a fixed text instruction for all query images. We demonstrate this capability in tasks like zero-shot sketch-based image retrieval, ZSSBIR, on benchmarks like 2Berlin, Sketchy, and Quick Draw, where our models outperform prior methods significantly. We report MAP and precision metrics for these benchmarks, showcasing the generalization capability of MagicLens models. Section Summary. In this section, we evaluate MagicLens' multimodality to image retrieval ability through tasks like composed image retrieval, domain transfer retrieval, and conditional image similarity using benchmarks like CIR, SURSO, and DTIN. MagicLens models, especially COCA-based MagicLens L, outperform previous models significantly on open domain benchmarks like SURSO and DTIN, showcasing their strong capability. Additionally, MagicLens models show consistent performance improvements across benchmarks, indicating the high quality of the constructed data and the scalability of the model architecture. Section: Text-to-image retrieval. In this section, we delve into text-to-image retrieval. We have developed MagicLens models that rely on vision and language encoders. These encoders, once trained, can be repurposed for tasks like image-to-text and text-to-image retrieval. To assess the effectiveness of MagicLens backbone encoders, we conducted evaluations on Flickr 30K and MSCOCO datasets using the same methods as previous studies. Our results, as shown in the table, indicate improvements in text-to-image tasks across all metrics on both datasets. However, we noticed slight decreases in image-to-text tasks. These findings suggest that our training approach can enhance backbone encoders for text-to-image retrieval. Similar conclusions were drawn with CLIP, as detailed in the table. The enhancements may stem from the need for a deep understanding of text instructions in our multimodality to image training task, thereby improving backbone language encoders. These text-to-image results demonstrate that MagicLens can effectively handle various forms of image retrieval tasks with strong outcomes, considering its performance on other tasks mentioned earlier. Moving on to data analysis, we compared our data construction efforts with previous ones like CompoDiff and InstructPix2Pix, IP2P. These prior methods used synthesized image pairs and template-based instructions for training image retrieval models. By using natural images and template-free instructions, our MagicLens model outperformed variants trained with IP2P data on all benchmarks. This highlights the strength of our data in enabling robust image retrieval models. Even when compared to CompoDiff trained with IP2P, our model showed superior performance on certain benchmarks. The visualizations of instruction keywords in IP2P and our data further illustrate the differences in keyword distribution. We also explored the impact of data scale on models by training MagicLens on varying dataset sizes. The results indicate that as the data size increases, the model's average performance improves significantly, emphasizing the importance of scaling data. Additionally, we investigated the effects of instructions on models by comparing template-based and template-free instructions. Models trained with template-free instructions consistently outperformed those with template-based instructions on all benchmarks, showcasing the effectiveness of naturally expressed and diverse instructions in enhancing model performance. Furthermore, we analyzed the relationship between model size and performance across different benchmarks. Despite its smaller size compared to other baselines, our MagicLens model achieved better performance, demonstrating high parameter efficiency and the strength of our data and enabling strong yet compact models. We also examined the impact of contrastive loss and model architecture on model performance, highlighting the importance of differentiating similar images and the significance of the model's design in achieving optimal performance. Section Summary. In this section, we explore the effectiveness of MagicLens models for text-to-image retrieval tasks by evaluating the backbone encoders on Flickr 30K and MSCOCO datasets. We observe significant improvements in text-to-image retrieval tasks while marginal drops are noted in image-to-text tasks, indicating that our training approach enhances backbone encoders for text-to-image retrieval. Additionally, our data with natural images and template-free instructions outperforms models trained on synthesized image pairs, showcasing the advantage of our training recipe in enabling stronger image retrieval models. Section: Retrieval on 1.4M Open Domain Image Corpus. In this section, we conducted retrieval on a large open domain image dataset containing 1.4 million images. To make the simulation more realistic, we set aside these 1.4 million images as our index set, which is the largest retrieval pool used so far. We selected 150 images and grouped them into 3 categories based on the type of instructions associated with them: simple, complex, and beyond visual. Simple instructions point out only one visual difference, like the same product in different colors, while complex instructions involve multiple differences, such as examples of cars and bags. Beyond visual instructions aim to find images that have no visual similarities with the query images, like searching for different attractions. We compared our COCA-based MagicLens L model with the previous best model, LinCIR, which is available as code and both use VIT-L backbones. Human evaluators assessed the images retrieved by these models for each query to determine which model best followed the instructions. LinCIR performed well with simple instructions but struggled with complex instructions and failed almost entirely with beyond visual instructions. In contrast, our model successfully met various search intents expressed through all types of instructions, especially excelling with complex, 61.3 versus 24.0, and beyond visual, 80 versus 4.7, instructions. In a qualitative study, we presented top 1 retrieval results on the 1.4 million image index set. Even with complex instructions containing multiple conditions, such as examples of cars and bags, MagicLens accurately understood the search intents and retrieved the desired images. An example with muffins demonstrated that MagicLens could grasp non-trivial temporal relations between images, thanks to the diversity of relations introduced by naturally occurring image pairs. However, in the case of a 3D anatomy query, the image retrieved by MagicLens may not always be the most preferred, as the instruction focused on the head. This indicates that our model may provide suitable but not perfect examples when instructions are not clearly expressed. For more qualitative studies, please refer to the figures in the appendix. Additionally, a visual case study was presented on domain transfer retrieval using the DTIN benchmark. The text instructions in each domain were, "Find this object in domain," using the same query image. All top 2 retrieved results were correct, demonstrating the effectiveness of MagicLens in understanding conceptual image relations.